Pablo said, this is Ileana, and I would like to present to you today some advances in real-time earthquake response systems. In order to start my presentation, I would like just to give you a very short introduction, especially regarding what is seismic risk. It is basically the potential negative consequences of an earthquake, and it is calculated, it is composed by three main factors. The first is hazard, so where and how strong an earthquake could be. Exposure, that is the elements that are at risk, buildings or people. And vulnerability, that is refers to the how likely is the elements that are at risk to be damaged after an earthquake. So how can we reduce these negative consequences? There is a way that is called disaster management cycle, and it is a series of activities, mitigation activities, preparation, response, and recovery activities that the main goal is that of reduce the risk. It is a cycle because of the repetitive nature of these phenomena, earthquakes. Within this cycle, the response phase that involves activities such as allocating resources and emergency services to the damaged area, it is a key. It's a very important phase, because you can imagine that the faster and the more efficient is this allocation, more lives can be saved after this kind of events. And a tool that is used in order to support this rapid response is the rapid availability of this kind of maps that are damage maps that show the spatial distribution of the damage. For example, in red we can see where are concentrated the buildings that are more severely damaged after an earthquake. So if these kind of maps are available in a very fast way, let's say within minutes after an earthquake, and those are transmitted in some way to the civil protection authorities, you can imagine that it will be for them more. It will allow for them to have a faster allocation of the resources to the most damaged areas. So, in order to calculate this type of maps, first it's important to understand how the ground shaking after an earthquake, how much the ground shaked after an earthquake. And this is done by means, this is done typically by this procedure. When an earthquake happens, the seismic stations that are located in an area detect it, and they allow to calculate the key parameters in a very fast way, the key parameters of an earthquake, magnitude and location. These serve as an input for what is called ground motion models, that are empirical relations that allow to calculate, well, they are calibrated from past earthquakes, and they allow to calculate how much a point in the ground shake as a function of the magnitude, or, for example, the distance, the central distance of that point. Also, there is another standard approach is the use of shake maps that are representation of the spatial distribution of the damage. And in order to obtain this, the essential ingredient is the use of ground motion models, and they are constrained using the recordings from the stations that detected the earthquake. So this is the standard approach that is used. A quick review of this short introduction. When an earthquake occurs, the first minutes are of crucial importance, because it is where critical response decisions are to be taken. One of the tools in order to provide to the civil protection authorities are these damage maps, these ground shaking maps, and the main ingredient for them is ground motion models. So now that I have told you this with this in mind, I want to present to you some projects that focus on providing this type of information in a real-time way. so that the civil protection authorities can respond in a more in a faster and more informed way. So the first project I want to talk about is PAGER, that stands for Prompt Assessment of Global Earthquakes for Response. And it is a project that has been developed by the United States Geological Survey. And it provides real-time estimations on the casualties and economic losses following an earthquake that may happen everywhere in the world. And it works in a very summarized way like this. When an earthquake happens, it is detected by the local seismic network. A shake map that I just introduced is produced to model the ground shaking in less than 1 minute. And then the exposure data is gathered, for example, the building inventory of the area that was affected, the amount of people that is there, and so on. And then the total losses are estimated using empirical, semi-empirical, or analytical approaches depending on the amount of data that is available for the area that was affected by the earthquake. Then these total losses and total economic fatalities and economic losses allow to determine a given level of alert. Yes, a given level of alert. For example, if the losses, the economic losses, were not so high, maybe an alert color green could be issued, and it means that there is no need for any response action. But if it is color red, it means that some protocols for calling for international help should be activated. And this alert is issued to the people that is affected, and in order for them to, and also to the civil protection authorities for them to respond. Well, one of the, it doesn't change the slide. Sorry. Okay, so as I mentioned before, some within PAGER, different type of methods for estimation are used. However, the empirical one is the most broadly, the one that can be more broadly used, because they, in order to build them, it is only necessary to have data on fatalities and economic losses from past earthquakes, and it's not necessary to have daily building inventories or daily information on the building codes or something like that. I am not going to enter into details with this now, but well, if you are curious, maybe after the end of the presentation, we can go here. But this empirical estimation, I just want to say that it is very fast, and it allows you to correctly it is very efficient to be integrated into this type of systems, because it allows to calculate in a very fast way these estimations. This is the output of the system that is called one pager. It is a summary page that summarizes all the main parameters of the earthquake, and the total estimations that were done for that earthquake, and also the alert level that was assigned to that earthquake. The interesting thing apart from that here is that this output is obtained at most 30 minutes after the earthquake, and this information is given to the authorities, to civil protection authorities, and also to people that would like to that is like subscribe to this system. Then yes, just to highlight some of the main strengths of Pager, it is a nice project because a nice system because it is it has a global coverage. It has been already operational for more than 10 years, if I remember correctly. It is fast and it combines hazard, vulnerability, and exposure information in a using very well established methods. However, the limitation is that, as you could remember, they rely on shape maps. And why in ground motion models? And why I say that this is a limitation? Because when I explain a bit in general these standard approaches, you can imagine that the fact that these estimations depend on so few parameters, this could you could think that the complexity of how waves propagate in the earth crust and how they interact with the local conditions of an area may not be fully captured by these models. So this is a limitation. And also the other one is that sometimes there are not enough recording stations to constrain the shape map, and as a result, the estimation of the ground motion may be simplified a bit. And this is the reason. Here I am showing the estimation of the ground motion obtained by ShapeMap for the L'Aquila 2009 earthquake. And well, because of these limitations, currently there is other approach that's being explored in order to provide the ground shaking estimations, and it is called 3D physics-based simulations. And instead of relying on empirical methods, this approach numerically solves how wave propagate through the earth, and integrate realistic models of from the seismic source, how the fault ruptures to the propagation path, and also to the local site conditions, so that we can obtain more accurate ground shaking estimations. As an example, I have integrated here in the slide the ground shaking estimation for the same earthquake, L'Aquila 2009 earthquake, obtained with 3D physics-based simulations. Each much more less, let's say, simplified than the one obtained with ShapeMap. But of course, there is a trade-off. This type of methods require a lot of computational resources, and also they take a lot of time. So maybe these kind of methods are difficult to integrate to a near real-time ground shaking assessment. But still, there are projects that are exploring this, and I now want to just present to you which are these projects and what they have achieved. One key for this is the use of high-performance computing resources, because those, in order to produce these simulations, we need supercomputers, high-performance computational infrastructure. Without this, the possibility to carry out near real-time simulations with this accuracy may not be achieved or possible. So yes, the idea is of the system that I am going to show to you is to imagine that an earthquake happens, and then at the same time there is a digital twin of this earthquake being built and being simulated, so that when the earthquake finishes, there is in a matter of minutes there is already an accurate estimation of the ground motion, and then the subsequent estimation of the damage. The first project that I want to talk about is Jurgen Computing Integrated Services for Earthquakes, and it has been developed by the Barcelona Supercomputing Center. It is a workflow that coordinates these near real-time physics-based simulations on high-performance computing infrastructures. And how it works? Well, in order not to repeat the the workflow that I am going to explain to you, it's basically the same that for the other projects that I am going to present. So this type of systems work by first automatically detecting large earthquakes, because these systems are connected to different seismic networks in order to from different parts of the world in order to detect these earthquakes, and then calculate characterize the main parameters of the, for example, of the source and of the area, the properties of the earth that was affected. Then there is a need to ask for the high performance resources. So this is also part of the workflow. The preparation of the input files that should be given to the software that will carry out the physics-based simulations. And then there is the physics-based simulation itself. And finally, there is a post-process, the need of post-process this data in order to produce this type of maps that will be the ones used by the civil protection authorities, for example. One thing that I want to say about this system is that it ends in the ground shaking assessment. It doesn't provide, for example, estimations of how many buildings were damaged or how many casualties are expected. It ends only on how much the ground moved. And the idea is that, again, this workflow is completed in minutes or hours, depending on the frequency that is desired to be propagated. You can imagine that the higher is the frequency to be propagated in the model, the finer should be the mesh, and the cost of this is much more computational time. And the software that is used by this particular workflow is Salvus, that is a spectral element code that is used for within this workflow. And just to highlight that this system can produce a simulation to propagate up to 5 Hz, which is, let's say, a nice number, because usually these type of simulations can accurately propagate from 1 to 8 Hz. So 5 Hz is, I would say, a nice number. So it can produce a simulation on a large domain, 100 by 100 kilometers, in just 1 hour and 20 minutes, which also is good time. Yeah, it's a short time. Yes, so I will just pass to the next system that is called ROS. It's also for real-time earthquake simulations, and this time this focuses in Taiwan. And why Taiwan? Because it is located in a very seismic area where two tectonic plates collide, the Eurasian plate and the Philippine Sea plate, producing a lot of seismic events in the area. So this, and the fact that Taipei, that is a highly populated, densely populated city, it is located on a basin. And basins are characterized because they can amplify a lot the motion, making the earthquakes very, very dangerous. So that is why there was a need of creating a real-time ground motion predictor, let's say. And this is why ROS was created by the Institute of Earth Sciences at Academia Sinica in Taiwan. And again, it is a workflow that runs 3D physics-based simulations. The specific software that they use is called the SpecFem 3D, that is also a spectral element code. The workflow is exactly the same. It's basically, essentially the same that what I have just explained. And this workflow works such that it can produce a simulation for the entire Taiwan in just 3 minutes. And you may think that 3 minutes it's very few short amount of time. And this is with respect, if we compare it with the 1 hour and 20 minutes that the previous project took. But the reason for this is that instead, as this is a project that is only it only focuses on Taiwan. The mesh, for example, the 3D model can be built once, and in real time it can be read, and that's it. It's not necessary to create it or mesh it. Just the data for this mesh and this model is read in real time. The problem is that this mesh has a very rough resolution. It can propagate frequencies only up to 1 Hz, which is not, it may be good for large-scale ground motion estimation, to have an overall pattern of the ground motion, but not for predicting, for example, structural damage. And just to highlight here that this project has an online simulator that we can consult, we can use, we can explore how changing the different parameters, such as the ones that are here, the magnitude, the location, what is the effect of this type of changes. Yeah, so finally, I want to talk about UrgenShape. That is a project that also focuses on 3D, near real-time 3D physics-based simulations, but this time located or focusing on the Friuli Venezia Giulia region that is in the northeast Italy. My PhD project is related to this, has contributions to UrgenShape. Just to give you some context, this region has an already operational infrastructure, operational system that provides near real-time earthquake damage assessment. It provides with this type of damage scenarios, damage maps, the distribution of the damage within the buildings in the region. However, it relies on shake maps in order to provide the ground shaking estimation. So this system has been developed by OGS, that is the National Institute for Oceanography and Applied Geophysics, and they also, with the aim of improving this workflow, have developed UrgenShape, that is a workflow such as the one that I have just presented, that aims to replace the shake maps and then instead use physics-based simulations, explore the use of physics-based simulations. The necessary high-performance HPC resources for running, for implementing UrgenShape and the physics-based simulations within this workflow are provided by Terabyte, which is a national project that aims to connect all, let's say, all the high-performance computing infrastructures in Italy, so that there is a strong network with which there is a possibility to carry out powerful and demanding tasks such as this one. So yes, here is where my PhD project enters in. The main objectives of it is to resolve some current challenges in making UrgenShape fully operational, because right now, for example, well, the original proposal of UrgenShape was taking a lot of time in order to carry out the simulation. So one of the main objectives is to reduce these computational times, and the second one is to develop a 3D model that can capture all the properties of the region. And finally, also it can be, the goal is also to improve this model, the impact assessment model, so that ultimately the damage scenarios, the damage estimations could be more accurate, as accurate as possible. Yeah, the engine of behind UrgentCheck is the code speed. That it is the code that is used in order to carry out the simulation, and it has been developed here at Politecnico di Milano, and it's an open source code that was designed to simulate large-scale seismic events in 3D complex media. I have here also inserted the link for the website of the project in case you want to have to take a look and to explore more deeply the advantages of speed. But I would say that the most important advantages, well, not important, but the reason why it is advantageous to use this into UrgentCheck is that because it again allows to handle 3D complex media and heavily exploits parallelism. So thanks to this, the simulations can be faster. The idea, just to focus a bit more on what is UrgentCheck and focusing on the ground shaking assessment within the large the large workflow, is to replace shake maps by the use of physics-based simulations. So UrgentCheck takes part now, and the workflow, I also won't enter into many details. It works essentially the same as the other projects that I have just explained. The difference here is that, as I mentioned before, this type of simulations are richer in the low frequency range. This is due to the discretization, the barriers, let's say, of the discretization of the mesh. Sorry. These low frequency components are provided by speed, as I said before. And in order to enrich, to obtain a waveform that is also that includes accurate high frequency components, there is another code that is used by this workflow. That is a 1D code. It works with stochastic methods in order to provide with the high frequency components of the waveforms for the simulation. So there is a creation of the input files for both codes. Both simulations are run in parallel, and then in the post-processing phase there is the stitch of the low frequency and high frequency components to end with plotting and calculating the damage maps, or sorry, the ground shaking maps. This is where UrgentCheck ends, and then this output is transmitted to the next stage of the big workflow of damage assessment of the region, the yellow one here. So without entering also into details here, I just wanted to share with you that in order to resolve one of the main goals of one of the main challenges of making UrgentCheck operational, we have proposed and implemented a new model setup technique strategy in order to reduce the time that it takes to create the model. That is the part of the simulation that takes most of the time. And I wanted to share here that within the original UrgentCheck workflow, the model preparation time was taking, for an earthquake of magnitude 6.4 that happened in the area. The time that it took to create the model was 21 hours. And with the new strategy that was implemented, this time was reduced to only 6.5 minutes, which is a very big improvement. Then for another earthquake that also was tested, magnitude 4.2, the time for preparing the model in real time was reduced from 3.5 hours to 51 seconds, which it was also a nice result. So just going forward, the speed simulation that it took, for example, to carry out the simulation for the 4.2 earthquake was 6.8 minutes using the supercomputer Leonardo that is here in Italy. So in total, we can say that 8 minutes it take to carry out the simulations, which is real, where it was very promising because it shows that we are really moving towards real-time physics-based simulations. Yes, and with this slide, I just wanted to highlight that the model creation is still under development. It is a challenging task, I would say, because it is necessary to gather all the necessary data, make an appropriate literature review in order to choose the set of properties that will represent the entire region in an accurate way. But yes, I won't enter into details. And that would be it for my side. That would be it regarding my project, regarding the projects that I wanted to share with you. And I hope that with this talk, you had at least a broad idea of what is being developed in the world, and that tools like pager, roles, urgent shake all contribute to faster and smarter emergency response with the overall or the ultimate goal of reducing seismic risk in areas. Yes, and that will be it. Thank you a lot for your attention.
Thank you very much, Ileana. If there are any questions